Welcome to Programming in Modern C++. We are in week 7 and we are going to discuss module 34. In the last 2 modules, we have been discussing about cast operators in C++ and how to use different cast operators in different semantic context. So, in the last module specifically, we have discussed about static cast, which is which can be used in place of any implicit casting conversion, or also additionally for upcast, also for some of the reverse conversions which are not implicitly allowed, risky, but can be used for downcasting as well, and particularly is useful to invoke user defined cast operations in terms of constructor or explicitly written cast operator. And we have also studied about reinterpret cast, which is basically reinterpreting a value which in simple terms mean that erase the type of the source and put the type of the target, right? Not recommended, not advised, possibly the only context you use is when you have to convert a pointer to an integral type or the reverse. In the present module, we are going to continue on this discussion and understand that the dynamic cast and typeid operator. Dynamic cast, as we will see, is a runtime casting operator, which is very unique and different from the other 3 that we have discussed. So, in this context, we will also take a look at what is known as RTTI, run time type information. This is the outline which will be available on your left. Quick recap from module 32 of what we have been doing. We have gone over this a number of times. We are now here to talk about the dynamic casting operator. So, what is dynamic casting? Let us start with a few, let us define the playing field. It can be used only with pointers and references. Dynamic casting cannot be used on objects directly. You can use it only on pointers or on references, everything else is a compilation error. It can be used with void star also. The purpose is to ensure that when you dynamically cast one pointer to another, the source pointer is pointing to an object. It has a type. The destination pointer, target pointer, will continue to point to that same object, but with a different type. So, dynamic cast ensures that this conversion gives you a valid object. If I was pointing by a type pointer and I dynamically cast it to a B type pointer, then dynamic cast ensures that the pointer actually is pointing to an object which can behave as B type. That is this guarantee is the most important. Right. Naturally, this will include conversion which are upcast. The upcast will always satisfy that, though it is not advisable to use dynamic cast for upcast operation, because dynamic cast is far more expensive. For upcast, you always have the static cast. Dynamic cast can actually be useful, or is the only context where it is useful is when you downcast. When you downcast, you are coming from a generalized class to a specialized class. So, you do not know, standing with a pointer of generalized class, as to whether the object has enough information of the specialized class. If it does, then this going down is valid. If it does not, then this going down is not valid, this casting cannot be done. This is valid for polymorphic classes, that is those with virtual member functions, at least one virtual member function. So, which could be the destructor, as we have seen. And it is valid if and only if the pointed object is a valid complete object of the target type. Right? So, that computation is the most important thing in the dynamic cast. If it is not, then the dynamic cast will return a null pointer. Otherwise, it will return the valid pointer value. It can be used similarly, as I said, with reference type, and it gives you a reference of the new specialized class type. And if it is disallowed, if the conversion is not possible because you do not have a correct object, then certainly since there is no concept of a null reference, it will throw an exception. There is a system defined exception called bad cast which is thrown. We have not yet discussed about exception. So, maybe you are you will not find all of the code here easy to digest, but you can come back to it after you have done exceptions in the next week. Dynamic cat can also perform other implicit casts on pointer. For example, it can cast null pointers between pointer types, casting any pointer of any type to void star and so on. So, these kind of tasks can also be done with dynamic casting. I think example is what will make things better. So, what do I have? I have a class A. Specialized from this, I have class B, class A, class B. Members and all that I am not considering, because that's not important. It's just the type which is important, right? And this is all of the classes are polymorphic, because I have a virtual destructor here, and since B is a specialization of A, naturally it has a virtual destructor. So, these are all polymorphic, and I have a class C. Class C is not related to this. This context is important. You know? So, now let us think. Let us say this is, I have a pointer P B which is holding the address of a B object. I have kept the naming consistent, so that you do not have to look up what is the type. If it is small b, it is a B object, if it is small c, it is a C object, and so on. Now, I dynamically cast, now I am dynamically casting this to this P B to A star. It is a B type of pointer, but it is actually holding a B type object, and I want to see whether I can hold this object by a type pointer, or in other words, whether I can think of this object as an A type object, which is basically the task of upcast, right. So, if I do that, it will be valid. So, here as we go with each C out, you can see the output written here. So, this is the first line of the output, this is your original pointer value in some machine where I ran, and you get the same pointer. So, this was the value of P B, this is the value of P A, and it prints upcast is valid. Right. So, first thing is done, that I can do upcast if I really need to. Second is I have done an implicit upcast by taking the address of the B object and putting it as A type pointer. Now, I want to come back. So, A type, the pointer type is A, the actual object it is pointing to is B, and I want to see whether I can hold it as a B type pointer only if it is actually a B type object, which it is. So, if I do this, this is the case of downcast, and again you will see that I get the same pointer value, the downcast is valid in this case. Right. Now, this is in PA, I have A object and I want to downcast to B, come from here to here, downcast in B. So, if I try to hold it by PB, which is a B type pointer, then I expect a B object, but it actually is an A object, which is a generalized object, which will be wrong. So, now this downcast will be invalid. How do you see it? This was your original pointer of A object, and your result of downcast, the result that the downcast returns you, the return value of downcast is 0, it is a null pointer. This null pointer tells me that the downcast is not right, I do not have a correct. So, by checking if the return pointer is null or not, I can ascertain whether the downcast has correctly happened or it is not possible to downcast. Right. So, this is the beauty. If you had used static cast here, you would have forced the casting without knowing that you are actually doing something wrong. The third, the next example, fourth, is I have taken an object of the unrelated class C and put it as a pointer. Now, from this A pointer, I want to check whether I have a C type object, but they are unrelated. As you can see, these are unrelated. A and C, these are unrelated classes. Naturally, there is no upcast, downcast, nothing can be defined in these terms, and the dynamic cast operator will rightly identify and give a null pointer as returned. So, this is a case of unrelated cast, which is invalid. So, PA was given, but PC will be, PA was given, PC will be null. You can see the dynamic cast is how powerful it is. It can really act as, and all these are happening at the runtime, because you have no way of knowing these things at the static time, at the compile time. Now, specifically if the pointer is null and I am trying to, what I am doing here and what I am doing here is the same, only difference is here the pointer is null. If the pointer is null, then it is a valid cast. Though since the pointer originally is null, the dynamic cast will return a null, but this is a null on success. It is a valid cast for unrelated types as well. So, you can use that in building up the logic. Now, let us take an PA to point to an A object and use dynamic cast to cast the pointer to void star, that is forget about the type, which means forget about what that object might have. Right. So, this is casting to void, which is valid. So, this will give you the same pointer back, telling you that well, you have been able to cast it right, and now you hold the object as a void type. Right. However, you cannot do the reverse for obvious reasons. If you have a void type pointer and you want to say, okay, let me think that this has got an A object, you cannot do that, because it is given a void type, the dynamic cast does not know how to find out the type information of that object. Right? It has to do it at the runtime. So, it has no way of knowing that. Since it does not know that, it cannot give you a conversion. So, here it is not a question of error, this is a question of an invalid expression, because dynamic cast cannot even operate on this. So, this is a static time compilation error is what you will get, and you have this kind of something like invalid expression type for dynamic cast. So, dynamic cast can cast to void star, but cannot cast from void star. Right. So, let us look at the same example, but here instead of using pointer, we will be using reference. I said dynamic cast works for both of them. So, this is a reference. I have also named the references easily, so that you can make out. So, RB1 is a reference to a B object, and I use dynamic cast to change to create a reference to a object, right. Obviously, B to A upcast, this is valid. I take a B object and create a type reference to it, which is implicit upcast. And then from that A type reference, I want to go back to the B type reference, that is downcast. In this case, the object was valid, so this also is valid. I have a type reference to an A type object, and I try to downcast it to a B type, which is wrong, because the actual object is of A type, the reference is of A. The reference is actually to an A type object. So, this is an invalid downcast. So, I get a message like bad dynamic cast. Take the unrelated class, I take the unrelated class and kind of force its cast its reference to A type, because I have to force, because they are unrelated, and then I try to dynamically cast back to the C type, which obviously is unrelated class. So, it is also something which cannot happen, which cannot be accepted. So, therefore, it also is an error. Now, you have a point to note in these two later cases where I have error, like in these two, that since this has to return a reference here, right, and it cannot return a null. So, how does it exemplify the failure? That is in terms of this what is called the try catch block, that you put the code within the try catch pair of curly braces, and if this particular operator code has some error that it cannot continue and give me a reference, then it will throw an exception known as bad cast, which is caught by this mechanism. So, this is the exception mechanism. We will talk in detail about it, but that is how the flow is working here. So, it is coming from here to here, because the error has happened. If the error did not happen, then the code will simply go through. Actually, these also we should put under try catch. I just wanted to keep things simple, because in these cases the exceptions will not be thrown, because things are all okay. So, this is how to deal with downcast with references. So, we have seen how to do casting on a hierarchy, particularly downcast, using the downcast operator with either the pointer or the reference of an object. Now, in this relation, so what are we doing in the downcast? In the downcast, we are certainly not only checking the type of the pointer or the type of the reference, but we are checking the runtime type of the object, right. We have talked about static time type and runtime type. So, how do we check that runtime type? So, for that the system has to have a small runtime system which runs along with our code, which is called the RTTI, runtime type information. So, what the dynamic cast does, it actually when it gets the pointer or reference to an object, it consults this RTTI to check on a particular object corresponding to the given object, which is called the type info. Right. This type info has all the information of what type the runtime object is in. Right. So, it is used only for the dynamic type of polymorphic object, that is the basic target, because if it cannot be used for the static type, because static type is compiler decided and static type information is not managed by the RTTI. So, there will be no information on that, but it is about the dynamic type where you have particularly polymorphic object is where you can get this type ID operator, put this operator to tell you in some way that what is the type. Right. So, it can be applied on a type or on an expression. So, this type ID operator actually gives you access to this type info structure, which as you can see is defined in the standard library under the std namespace. So, what you can do? You can basically compare two types. You can, for equality and inequality, naturally less than greater than does not make sense, and you can invoke a name member function which gives you a user understandable text representing the name. Now, the point to note is this is implementation defined, that the standard has not specified how to name the types, because actually the types are defined by the user, and how the system will represent it is up to the compiler implementer. So, if you are using type IDs, you have to look at the documentation to know how the types are named, so that you can correspond them to your source code. We will see examples. It works for a polymorphic type only, and if a polymorphic object is bad, right, it is not a proper type or something, then it will again throw a bad type ID exception, which is defined in the standard library. So, first let us try to look at how to use the type ID operator on a polymorphic hierarchy. Right. So, very simple, I have A and B. Specialized from that, A has a virtual destructor. So, all objects of A and B are polymorphic. I create an A object, I ask what is the type of A and the pointer to A, and these are the names that I get. It is class A and it is class A star. I create a pointer to the A object and ask what is the type of the pointer and what is the type of the pointee. I get class A star, class A. This is how you can actually. Now, most often you will not need to do this. Your virtual functions, polymorphic dispatch and downcast operator will take care of all the runtime types, but in case you want to go deeper and really want to find out what is the type you have and so on, you can make use of this type ID operator. I would presume that normal application development programmers in C++ would never need to use this, but this is to give you more debugging and exploratory strength. Now, I have a B object, I print B and the reference B and B star. I do an upcast, remember pointer A is of type A, I do, you can see that the pointer type is A star, that is how it is defined. I have done an upcast, so the original object is of B type. You can get the entire picture here through this. This is with the references. If you do this R1 and R2, R1 is a object, R2 is actually reference of a B object, but held as a type reference. You can see it rightly says that this is a object and this is a B object. So, this is how the type ID operator can be used, and this is how you get. I have here you can see that I have given two sets of outputs. This is what I found on my Microsoft Visual C++ compiler, which is kind of more understandable, and this is what I found on the online GDB. I said that it is implementation dependent, it is implementation defined. So, for example, you can see here that in every case the class name is just marked by 1 and pointer by P1, and then that given name in the source that comes up, right. So, that is, so you have to check your documentation, the documentation of the system, and know how to decipher these names. Next example are staff salary code that we had. So, just I just put in the staff salary, I put the type ID of the staff I. Staff I is an array of is an element of the array of pointers, each is of type engineer, but they are pointing to different types of actual objects. So, if I dereference, I should get a different object. So, that is what I get, that for the pointer I always get engineer, but for the object I get specifically engineer, manager, director as I have put. This is how it comes in terms of the online GDB system. This is how they mark the type names. Good fun. Now, you can use it partly for non-polymorphic hierarchy also, though it may not make much sense. For example, here I have x object and its pointer. I have x object, address of x object put to a x type pointer. I get this, which is, I have y object. So, this is a hierarchy, but it is not polymorphic, right. The y object, I do this, I get class y. I do an upcast y object to the pointer of x object. So, I have done an upcast and I try to do this. I get x star and I get x object. This is because it is non-polymorphic, because as you know, if it is non-polymorphic, then the compiler has to decide everything based on the static type, right. So, star q has a static type which is class x. Earlier, when this was polymorphic, then I would have got y here because the runtime type is y, but this hierarchy is not polymorphic. So, I cannot get that. So, because of this, the value of finding type ID on a non-polymorphic hierarchy is marginal. Right. Similarly, you can do this, you will see the same thing here in terms of the reference as well, and different types of names for the online GDB system. So, if the type IDs are bad, then it throws an exception. So, this is fine, type ID star A, again the context is the same and this is a polymorphic hierarchy. So, if I do star type ID of star P, I get this. If I now I have done this, I have deleted the object. So, I was holding the A object, I have deleted that. So, when I do type ID for P A, the pointer, I still get class A star, which I should. But when I do star P A, this is an invalid access because the object is already gone. So, I get this kind of a message on MSVC++ that access violation, no RTTI data. Now, I set PA to null. Again, the type of PA is correct, but when I try to check the type for the type ID of star PA, I am doing a null pointer referencing. So, I get a corresponding error, right. So, this is what I are caught by this exception. So, these are the cases, I mean some of the cases where bad type ID might get thrown because you are using the type ID on a bad object or a non-existing object and so on. Interestingly, on online GDB, you just get the correct values, correct results. You don't, nothing is printed for the errors that are produced. It may be the settings of the GDB. I really did not check further on that, but be careful, check on the documentation before you proceed. Now, I will not go into the depth of RTTI, it is a very deep subject, but I just want to tell you that all this is possible because you can say a runtime system is helping your program to find this. And in terms of a polymorphic hierarchy, in terms of a non-polymorphic hierarchy, we have seen that it has hardly any value. In terms of a polymorphic hierarchy, if you ask yourself, really where is that information of type coming from? It is very simple. We have learnt about the implementation of virtual functions. So, what does a virtual function need? It needs that the class has a unique virtual function table, and every instance of the class has a pointer to that class specific virtual function table. So, what the RTTI does in a gross abstraction, this is not the exact thing, but in gross principle what the RTTI does, it maintains a catalog of the different classes that exist which are polymorphic and their virtual function table pointer value, because that is a unique identity of any object of that class. And so, whenever an object is given to RTTI either through downcast operator, through the pointer or reference, or through the type ID operator, if it is a polymorphic object, it will have the naturally the pointer to the virtual function table. RTTI looks up the catalog of classes and the corresponding virtual function table pointer values, and wherever it finds a match, it knows that this is the original class of which this object belongs, and that is the type runtime type of the object. So, that is the basic functionality of the runtime type system in a very simplistic term, but in terms of an effective understanding that actually the virtual function pointer table becomes the identity of the type, which is then converted into its equivalent name and all that, and then you decide on the conversion rule. Does this type matches the target type that the downcast operator has asked for, and so on and so forth. But this in principle is how the whole computation in this, the backbone of the computation in this goes on. So, that tells you why on a non-polymorphic hierarchy the dynamic cast or type ID has no meaning, because since in those there is no virtual function pointer table. So, RTTI catalog has no registry for that. RTTI registry is blank about those objects. So, all that you can infer is only from the compile time type, which is the static type, which should be always dealt with the static cast operator, not with the dynamic cast operator. So, that concludes our discussion on casting that we have been continuing from the last two modules. So, this was the third part, and we have studied the dynamic cast type ID operator and the runtime type information. Thank you for your attention. We will meet again in the next module.